Hey everybody, Mr. Clausen here. Just wanted to go over the lesson today. The essential question we got going on for this video is why are Lewis dot structures useful and how do you go about drawing them? And I find that often the best way to go about learning this new topic is for us to review what we already know. So where we're going to start then today is we're going to draw the Bohr diagram for element 20, which is calcium. So get your periodic table handy and go ahead and look on the periodic table and see if you can find calcium. So I have one over here on the side, and if we take a look, there it is. There's calcium right here. It's in the second column and fourth row, and sure enough, if I zoom in a little bit more, we can see that yes, it does have an atomic number of 20. Now, what does this mean when it came to drawing a Bohr diagram? Well, this means it's going to have 20 protons in the nucleus. And then if we take a look at the mass number, we can also see that if you have 20 protons and then you have 20 protons and neutrons, you subtract it off. It's also going to be 20 neutrons in there. Okay, neutrons. But the more important thing when it came to Bohr diagrams is the fact that because we have 20 protons, we're going to have 20 electrons. So Bohr diagrams were all about drawing the number of electrons. So what we're going to have to do is go around here and put, all 20 electrons around it and fill up the energy levels as we go. Now, we could do that. We could go one by one and work our way out. We've done that before, but let's take a look here and review some of the trends we learned in the last unit. So looking back at the periodic table, there's calcium. What do we remember for the number of energy levels an atom has based on its location? What we should be thinking right now is every time you go down the periodic table, you go down one row, it adds another energy level to that atom. And so since calcium here was in period 4 or row 4, that means that calcium is going to have 4 energy levels around it. And so it can be a little bit faster here if we just draw the 4 energy levels for the Bohr diagram. I'm doing some dotted lines. So that's number 3. And finally number 4. All right. So I've drawn my 4 energy levels. And if you remember, how do you actually move to the next energy level? Well, what you have to do is you have to completely fill the one before it. So in the first energy level, we can put 2 electrons. In the second energy level, it can hold up to 8. So in energy level number 2 now, I'm going to put 8 electrons. 2, 3, 4, 5, 6, 7, 8. Then we know in the third energy level, it also can hold 8. All right, so I'm going to fill that one up completely. And this is just because we remember that you can't move to the next energy level until you've filled it up already. And so what we could do is we could keep counting that up, but we got to remember this other trend that we learned on the periodic table, and that was that based on its location, so what group an element is in, that'll tell you how many electrons are in the outer energy level. It's the valence electrons. And so for calcium, since it's in group 2, it's going to have 2 valence electrons or 2 electrons just in the outer energy level. So we do that. Now, if you wanted to double check, you could go back and you could count them all up. And you would find out that, yes, we do have our 20 dots drawn around there for that Bohr diagram. Now, Bohr diagrams had their place. They help us understand some of the patterns that are going on there. But it is a bit redundant when you're coming in to learn chemistry to sit and draw all of these other circles, especially since all of these shells are completely full to get to the outer energy level. The only one that's really sort of unique for each element is the idea of how many electrons are in its outer shell. And so that's what we do with a Lewis dot structure. Lewis dot structures are only concerned with the outer energy level of the atom. So I'll say outer energy level only. All right. And so what this does is it simplifies it quite a bit for calcium. For calcium, all we'd have to end up doing is drawing just what's going on in that outer energy level or in that valence shell. So since calcium has 2 electrons there, the Lewis dot structure would simply just look like that. Just 2 electrons in it to go at this point. So a lot faster, right? Sorry, slid right up there. It's a lot faster to just draw the Lewis dot structure, and especially if you know the pattern, which we've learned, that deals with number of valence electrons, you can find that real quick right there. So let's go through some examples, because there is a little bit more to it, which I'll show you in the examples for how to draw the Lewis structure. But typically it'll only, it only matters once we start getting a few more. All right, so for this first one here, what we'll take a look is, let's take a look at the example of magnesium. So go ahead and find it on the periodic table. All right, so if we take a look, there's magnesium. It's actually in the same group as calcium is. So that is group 2, meaning that it has 2 valence electrons. And so magnesium, its chemical symbol would be Mg. All we have to do is put 2 dots in it, just like we did for calcium. All right. Let's go to the next one. Next one I have here on my list is to do boron. So find boron on the periodic table. I'm just giving you a second to look it up. You're going to find it. It's right here. Okay, so that's group 13. And what that means is the number of valence electrons we have, don't say 13. Sometimes people want to think that, but if we remember our pattern, it means it has 3 valence electrons, or boron has 3 electrons in its outer energy level, and so its dot structure would be a B with 3 dots around it, 1 for each one of the electrons. Okay. All right, now what I'm going to do is scroll down a few more to show us what's going on. Let's get to nitrogen. Nitrogen's where the little extra rule comes into place. So if you find nitrogen on the periodic table, it's in group 15, meaning it has 5 valence electrons. So when we do nitrogen, we draw the nitrogen, and then what I find useful is, imagine that you have, like, I always call it a box, but it's not a box, it's just a square. Imagine you put that nitrogen symbol in a square, okay? Or like I said, I always imagine it's a box. And the rule is, when you're putting the electrons on, you can only put 1 electron on each side of the box first. So if you take a look here, I'm putting 1, 2, 3, 4. And now that I have an electron on each side of the box, what I then do is, anytime you have above 4, which you will happen, is you go back and then you can partner it up. Okay, so what I say here is, let's see here, 1 per side at first. Then you can go back and double them up. Okay, it doesn't matter if you put the double dots on the top or the double dots are on the side. I tend to go counterclockwise. I don't know why, I just do. But here's an example of what would not be allowed for it. So if we were to say, take a nitrogen and go 1, 2, 3, 4, 5, you might think that that's correct at first because it's got the 5 dots for the Lewis structure, but it's just incorrect because you don't have 1 on each side of it, of that box. Okay. All right, let's do oxygen. Find oxygen on your periodic table. I'll give you a second to look for it. All right, hopefully you found out it's right there next to nitrogen. So oxygen is in group 16. That means it's got 6 valence electrons. And so what would the Lewis dot structure for oxygen look like? It's going to have 1 dot on each side first. You got to put 6 dots out there, 1 for each of the valence electrons. So far I got 4. And now what I can do is I can go back and partner them up. And like I said, it does not matter where you put them, as long as you got 1 on each side of the box first. So I decided to put mine on the top and then over here on the left, and that would totally work. Okay, let's go ahead and do sulfur. I'm going to remind myself where sulfur is. Oh, I should have known. If we take a look, there's sulfur. Sulfur is directly underneath oxygen in group 16. Let's go ahead and put that down. Sulfur is also in group 16. It's got 6 valence electrons. So what is the dot structure for sulfur going to look like? You guessed it, it's exactly the same thing. So you're going to go 1 per side first, and then you can go back and double them up. So in this case, I put my 2 dots on the top and the bottom and left my single electrons on either side. Okay, so that's how you draw a Lewis structure, but we haven't actually got to the point of, like, why can this be useful or helpful to draw these Lewis dot diagrams or these Lewis structures for it. So here's what we I like to bring up. So for example, we just did this one. Here's the Lewis structure for oxygen. It's got its 2 pairs and then 2 lone electrons. And I don't know if you've ever asked the question, but why do we call water H2O? I mean, other than that's just what it is, but why is it not like H4O or H5O? Or why is it not, you know, H2O3 or something like that? And the Lewis structures can help us out with this. So when we look back at oxygen, we got to remind ourselves how many electrons is what is considered to be stable for atoms. So oxygen only has 6 valence electrons, and so it leaves 2 gaps right here that it's looking to fill because it's trying to get to that 8 valence electrons on the outside. And so I'll just bring a hydrogen in a different color that works. What happens is if you bring a hydrogen atom in, hydrogen only has 1 valence electron. That is not a good color for that. We'll switch this and just do it in black now. You bring the hydrogen in. The hydrogen has that 1 electron that can go into that spot. And then you bring another hydrogen in, and you can put it in that missing spot. And now all of a sudden, if we take a look at the oxygen, around the oxygen there are 8 electrons, which is considered the stable electron configuration. And it's doing this because it's sharing its electrons with the hydrogen. Hydrogen's also trying to get that stable configuration of having 2 electrons in its outer shell. And so what they've just formed here is the chemical bond that we always talk about. Now, if you wanted to know why is it H2O and not like H5O, it's because you only need 2 hydrogens to fill in those missing gaps around the oxygen. And so that helps us figure out why water is H2O and not, say, H5O, for example. The other thing that's useful about dot structures is they also help us figure out what the molecule might look like. And so you never will see water listed like this, you know, H-H with the H in the middle and then O on the outside. Whenever I draw a water molecule, all right, in class, I always draw it like this, and I know you've seen it everywhere else, where it kind of looks like an upside-down Mickey Mouse, or just depending on which way it is. But they always have the hydrogens over here and the oxygens over there. And where that's coming from is it's coming from the idea that the hydrogens bond to the oxygen, and it helps us predict what this shape is. Okay. The other reason it's bent too is because you got those extra electrons on the other side, and they actually do a little bit of what's called repelling, and so they're repelling the hydrogens away to push it all out. But my point here is why are dot structures useful? They can allow us to help us predict what the chemical formula for something is going to be based on how many electrons are open. Okay. The other example I have here is carbon over on the right. And carbon is an extremely important molecule. In fact, there's a whole branch of chemistry dealing strictly with stuff that's made of carbon. It's called organic chemistry. But why carbon is so useful is the idea that when you look at its Lewis structure, you can see that it's got 4 valence electrons, but it's also then looking to make 4 bonds because it's missing 4 electrons. So what we can do is if we bring in a hydrogen in each one of these cases, those hydrogen atoms go in and share their electrons with the carbon. And then from the carbon's perspective, it's happy to share that because it's now got 8 valence electrons around it. This is also why we get CH4, which is this stuff right over here is how we'd show it. Instead of drawing the dots, we sometimes just signify that with a line to show the chemical bond. But this is the chemical in natural gas, and it's called methane. So that's what the Bunsen burners burn in the classroom. And once again, the whole point of doing this is not so that you can predict the shapes right now, but just seeing that there is a reason to learn the Lewis structures, and that once you understand what the Lewis structures are doing, they can help you predict what the shape of the molecule might look like, or help you predict what the chemical formula might be. All right, so that's the lesson. What we've taken a look at so far is why are Lewis structures useful? We just went over that, and how we draw them. Remember that for a Lewis dot structure, to draw them, it's the outer energy level only. You can figure that out based on its location on the periodic table for how many valence electrons it is. And then the only other little thing you need to worry about sometimes is that we want to make sure that when you do this, you do 1 electron per side first. All right, if you have any questions, please reach out to me, and I'll talk to y'all when I talk to you.